Let's deep dive into the topics. So I'll be talking about deep learning for causal inference and how we use it in the context of promotions. So here's the presentation agenda. So first, I'll be giving a short introduction on the field of causal inference, which is actually a field that's been, I would say, it's been as old as statistics as general. Then I'll be talking about the deep learning application to causal inference. And I do want to apologize in advance to the non-technical audience, to the audience not familiar with deep learning. It's going to get a bit technical. And if I haven't completely lost you by the presentation, I'll have a few more exciting information for you at the end of my presentation. So yeah, let's get into inference and what actually it means. So initially, causal inference, the medical field. Doctors were really concerned with, if we give a patient a treatment, what will be the impact on the patient? And then what if the doctor doesn't? Then what will be the impact as well? But for good, actually, this is very interesting in the of marketing. So if we give a customer a promotion, for instance, we're interested to know how much more users will transact. And in that sense, we're interested in what we call incremental transactions. So let me give you an example of incremental transaction calculator. So let's say that Mr. K right here, and Mr. K right here with any promotion completed 5 transactions within a week. Then we have a parallel universe. And in this alternate universe, let's say that Mr. K was given a yellow promotion, and then he completed 8 transactions as a result of being given a promotion. And then if you do basic maths, transactions with promotion minus 5 transactions without promotion, you get 3 incremental transactions. I guess I already know what you're thinking. You must be thinking, yeah, but it's not really possible for now to access the alternate universe. So it brings the nature of the counterfactual nature of causal inference. As you can imagine, causal inference is very useful to identify users that are most sensitive to promotions. But it's actually counterfactual by nature, because if you think about it in your training set, we only have outcomes of customers with or without treatments. And by the way, I'm going to use the terms treatment and promotions quite interchangeably throughout the presentation. So if you hear me say treatment, think about promotion. And if you hear me say promotion, think about treatments. And as you can imagine, then because it's counterfactual, it's impossible to get the actual incremental transaction on an individual. And that means that actually we cannot use the more basic traditional machine learning algorithms. And what I mean by counterfactual is that if you take a look at this dummy data set, for instance, at the first row, we have one user that is assigned a treatment, and then we have its measured outcome. And then on the second row, this user was not given a treatment, and then we still see the recorded outcome as well. And as you can see, as you can imagine, there are a couple of challenges with respect to causal inference. And there are 4 main ones. The first one, which I'm going to be talking about extensively, is called the selection or confounding bias. And by that, this bias is actually created by the fact that we may get a data set where the treatments were not given randomly. And I'm going to expand on this later. There is a huge variety in available treatments. So we have different types of promotions. Like for Gojek, we may have discount percentages, we may have cashbacks, we may have price deductions. So yeah, quite a bit variety. And that entails the heterogeneity in treatment effects. So if you think about it, like some customers may prefer a discount percentage, while others may prefer cashback. So when we model this problem, our model should be able to take into account like this diverse variety of treatment and the heterogeneous reactions. And last but not least, there's also a hard validation. Because of the counterfactual nature of it, to basically gauge which model is better, you actually need to experiment with the causal inference model online. And that means that you cannot use traditional machine learning validation, such as trained test set or even cross-validation. And I do want to remind you that this is going to be a more technical presentation. So to get you warmed up, I'm going to introduce my first mathematical notations. So let's say that we have a variable t that takes the value 1 if the customer is given a promotion and 0 otherwise. We have x, that is a feature vector that is, I guess, traditional to any machine learning problem. And y is our measured outcome. So in the context of marketing, Gojek, that's the number of transactions, for instance. And the underlying idea behind causal inference is this one. So we have a treatment effect tau, which that is a function of x. And basically tau of x is the difference between the interventional expectation of giving a treatment and the interventional expectation of not giving a treatment. And for those of you who are familiar with statistics, this is slightly different from conditional probability. Because in conditional expectation, what you do is actually you're just modeling the joint distributions between two variables, sort of modeling the randomness between two variables. Here, you're not really modeling the randomness, you're modeling the sort of the intervention, which is not random, because you sort of have the decision-making power over which treatments you are going to give. So this is slightly different. Hence, this is why you see the do operator right here. And there are current state-of-the-art methods, such as double machine learning, doubly robust learning. I'm not going to be talking about these today, but I do encourage you to maybe look into these. So those are very general methods, but in practice, actually, they work mostly with like tree-based algorithm. Like think about random forest, or even like the boosting algorithm such as XGBoost, to estimate those treatment effects. But today I'm going to be talking about the high-sci model, which is actually one deep learning application to causal inference. So as I mentioned earlier, causal inference is a very old field. But the paper that I'm going to be presenting today was published in 2020, so quite recent, by Tata Consulting Research. And actually, the advantages of deep learning over the existing causal inference libraries is that, yes, you have to code everything from scratch, but at the same time, it's more flexible, so it's easier for debugging. And the advantage as well with the high-sci in particular is that, as I mentioned earlier, like if you have a wide variety of treatments, the default architecture of this model actually enables to account for this big variety of treatments. But before I deep dive into the model architecture, let me define more precisely the confounding bias, which I mentioned earlier. So a confounder is basically a variable that may impact both the treatment and the measured outcome. So if we go back to the medical field, for instance, let's say that you are a doctor and you may prescribe a drug based on the gender or even the age of the patient, because you want to cater to the needs of the patient. So the drug is going to impact the recovery, but let's say like the gender or the age is also going to impact the recovery. And basically, because the doctor used some features or some criteria, this is going to be a non-random allocation. And as a result of this non-random allocation, we often get a bias of the features towards the treatments in our training data set. And we're going to need to address this bias in order to properly estimate the treatment effect. And you may be wondering, oh, but what would be the confounding variables for marketing or promotions? So for instance, like let's say that you are a marketing team. Let's say like you have frequent users and you may prefer to give them promotion A, and for the non-frequent user, you prefer to give them promotion B. And yeah, that results into a non-random allocation. Here is the model overview. This basically HiSci consists of two networks. One is the decorrelating network and the outcome network. And I'm going to be explaining each of the building blocks of this model. But before I explain a bit more the architecture, let me get you started with the model inputs. So what it takes is a classical, I guess, feature vector X and a one-hot vector T that basically indicates the which treatment is assigned. As an output, you have a vector of k treatment outcomes. So for instance, the number of transactions. And each element of the vector records the outcome. So let me give you an example. So for instance, let's say that we have 3 treatments or 3 promotions in total. You have a sample that is assigned the second treatment. And then the outcome vector will look like this. So as the first element of the vector, you have 0 because it's not assigned the first treatment. Second element is 3.5, let's say 3.5 transactions. And then the third element of the vector is 0 because it was not assigned the third treatment. In terms of like neural network and layers and things like this, I do want to mention that those layers are a bit, I would say, boring. So there's no convolution, there's no LSTM. It's mostly dense layers. But what is interesting is actually different loss functions that we are going to use for the causal inference problem. So I'm mostly going to be talking about the different loss functions. And before I do that, before I introduce the encoder-decoder network that we'll use as the decorrelation part, let me do a toy example to basically illustrate the confounding bias. So assume that we have a treatment distribution of 3 counts of promotion. We have a data set of 10 features, and let's take a look at customer A. So the first thing that I want to introduce is my unbiased overall treatment distribution. So that's my normal distribution that is unbiased. I have a feature vector XA that corresponds to customer A. And what the confounding effect means is that the treatment distribution conditional to the features of customer A may be different from the original unbiased distribution of all treatments. So for instance, let's say that customer A may be biased to heavily to the third treatment, slightly to the second treatment, and not at all to the first one. The treatment distribution conditional to the features of customer A may look like this. So for instance, in the first treatment, there's a 0% probability that it's going to get it. Second treatment is slightly biased, so there's a 20% that is going to be assigned to it. And the third treatment is heavily biased, so let's say 80%. And what we want to do actually is that through this encoder-decoder network, we're going to learn a representation of the 10 features as a 5-dimensional vector. So I have my original feature vector right here. And I want to learn a representation phi of XA of 5 dimensions. And I'm going to learn this representation such that the treatment distribution conditional to my representation is slightly equal, is approximately equal to my original unbiased distribution. And so with this example, allow me to introduce my encoder-decoder network. Yeah. So through gradient descent, we are going to learn a debiased representation of our initial feature vector. So I have an encoder phi right here that basically takes a feature matrix of n samples and p features as an input, and then it outputs a representation layer phi of x of dimension n times l, where l is much smaller than p. And if you think about the previous example, p here would be 10 features, and my L here would be 5 features. And then I pass this representation layer phi of x into a decoder, psi. And what this decoder psi, it basically takes its representation and then it outputs a decoded layer psi of phi of x back to the original dimensions n times p. And then for those of you who are familiar with encoder-decoder networks, this is my first classical encoder-decoder loss, which is not very innovative. So if you take a look at the terms right here, what this is simply the L2 norm of the vector difference between the original feature vector and the decoded layer. Yeah. So if you're basically like what this enables is that my phi of x will keep a degree of similarity to my my original feature vector. But yeah, this is very classical encoder-decoder loss. This is not very innovative. The second loss function to introduce, and this is actually the function that's going to enable us to tackle the confounding bias, which I just introduced. So before I introduce this loss function, let me give you a few assumptions reminder. So my overall treatment distribution P of t is unbiased. But my conditional distribution for treatment, P of t given phi of x, is biased. So this equation right here is what we call the cross entropy measure. And the cross entropy measure is actually directly proportional to what we call the KL divergence. So the KL divergence is a distance measure between two distributions. And so basically the smaller the distance, the smaller the KL divergence between two distributions will be, then that means like, yeah, the less difference there will be between the two distributions. And in a sense, because the cross entropy measure is directly proportional to the KL divergence, if you are minimizing this cross entropy loss, it's as if you are sort of minimizing the distance between my unbiased distribution, P of t, and my P of t given phi of x. And this is how you make it, this is how you debias your conditional distribution in a way. And now you may be wondering, oh, but how do I get P of t and how do I get P of t given phi of x? So for P of t given phi of x, it's actually very standard deep learning procedure. So basically what you do is you take your representation layer phi of x and you pass that into a softmax layer. And for P of t, if you don't understand this fancy notation, don't worry about it. What this means is just that you are just counting the proportion for each treatment within your training set, and you basically get your treatment distribution. In blue is a regularizing function. I'm not going to talk about it, but it's actually quite interesting. So if you're interested in it, like feel free to just check out the original paper. But for the sake of brevity, let's skip it. And that actually enables me to introduce my first decorrelation loss function. And so just reminder, so the first term right here, LC of phi, is my cross entropy measure that enables me to debias my representation layer. My LAE right here is my classical encoder-decoder function, which is, yeah, which enables me to preserve a degree of similarity of the original feature vector. And I have my regularization term. And then beta and gamma are hyperparameters, which you can tune based on your preferences. And then for my final loss function, what the final layers are going to take as an input is a concatenation of two things. Phi of x, which is the debiased feature representation that we learned from the previous loss function. And then Tn is a one-hot vector that indicates the treatment recorded for sample n. And then for my outcome loss function, if you remember from the introduction slide, what I said is that the output of the neural network will be an outcome vector of size k treatments. So let's say that, you know, like you have 3 treatments in total, then your outcome will be, the outcome that you're trying to predict is a vector of 3 dimensions. So in the paper, let's say that you have yn, that is the original feature outcome vector, and then you have y hat n, that is the prediction for this outcome vector. And then you simply introduce an RMSE between each element of the vector. And that is actually very typical machine learning loss function to basically make sure that you predict your outcome well enough. And then the final loss function to minimize becomes this. So just a quick reminder. So my LC of phi is my cross entropy measure that enables me to get my unbiased representation feature. This one is the classical encoder-decoder loss function. This one is the regularizing term that I skipped. And then this one is my outcome loss function, which is a standard RMSE loss function. And then beta, gamma, and lambda are hyperparameters, which you can tune as well. Yeah. Sorry if it was a bit heavy. But if you found what I said very interesting, sorry, one more session before I move on to the GovTopper information. So if I give you the, if you remember earlier what I said, that the goal was to make incremental predictions, that the goal of causal inference is to estimate the treatment effects, meaning the difference between the interventional expectation and the interventional expectation of not giving a treatment. So how do we do that with the high-psi model? So first thing you have to do is actually including a control group inside your training set. Basically, you want to include people who have not been given any promotion to have that to generate your incremental prediction. So that would correspond to t is equal to 0 here. So you take a feature vector x of a customer, and then with a one hot vector that is indexed as the control treatment, you generate a control prediction. So that would be your term right here. And then with the same feature vector x and the one hot vector that is indexed as the treatment, so you generate a treatment prediction, this term right here. And then the last thing you have to do is simply to subtract this control prediction here from the treatment predictions, and you get your treatment effect. Yeah. So I hope I haven't completely lost you. But if you are excited about what you heard, and if these are things that you would see yourself working on, we actually have 2 open positions for GovTopper, and we also have for data scientists and also for analyst roles. So not just data scientists, actually. You can check them out on LinkedIn or Liver. And yeah, if you have any questions about what you heard, feel free to connect with me on LinkedIn at Kilian Tep. Yeah, so if there are any questions, yeah, I'm free to take them now.
Someone's asking, why are tree-based methods preferred for such applications? If you would like to answer that. I mean, if that's the case where tree-based methods are preferred.
That's a good question, actually. I mean, I don't know why. There are maybe like the short answer would be that those techniques have been around for longer than deep learning. Yeah, I don't have the answer. I just know that for me, like the only short answer I could give would be that yeah, I guess tree-based methods have been around for longer, for more traditional like sort of regression problems than structured data. And usually with causal inference, you deal with structured data. So I would assume that tree-based methods were preferred for such applications, yeah. And also like deep learning is, it was mostly used for computer vision, NLP. So I guess intuitively it doesn't really make sense to use it for causal inference, but now we do, yeah. How do you make sure that P of t estimated from the training data is unbiased? That's a very good question. It's actually an assumption from the, because P of t is an assumption from the paper. So what you can do, like there are some, if you are not really satisfied with the, I guess like the initial population distribution, is that, you can do like oversampling or subsampling until you get a probability distribution that you deem yourself unbiased. So the question, like, I think there's a bit of confusion between unbiased and unbiased and biased. So in a sense, you assume that the overall population isn't biased, but what is biased is actually the conditional probability. So in a sense, the conditional probability would be biased because, you know, like, let's say like a doctor, you know, is going to target more specific patients based on their genders and their age. So obviously, like, you don't expect the general population to have a treatment distribution for, you know, like, say like a senior person who is female. So yeah, that's the idea behind this. Yeah. Is significant testing finding p-value available for this method? No, it's not available for this method because you are trying to estimate the treatment effect. What you can do though at the end to see if you know, like, you have estimated it properly is that once you deploy your model to production, because once you deploy and you have, you know, like a targeted group and you have a control group, and the group that was targeted was the one with your model, you can actually see if you know, by making like the overall group, you can actually compare the two groups and then make hypothesis testing to see if your algorithm was correctly targeting those customers. But in the design of the algorithm, no, there is no such thing as p-value. Actually, A/B testing and causal inference are very, very related, in a sense that I mean, if I actually you know, like, go a bit outside of the scope of the paper I just presented, actually A/B testing is key for causal inference because the primary example, the primary use of causal inference was actually through A/B testing, in a sense that if you want to see if the treatment has an effect, you get a control group on, you know, like an A group, and then on the B group, you get a treatment group. So I would say causal inference in its most basic form is actually A/B testing.